Let's look at example 11 now. A small component in an electronic device has two small holes where another tiny part is fitted. In the manufacturing process, the average distance between the two holes must be tightly controlled at 0.02 millimeters. Else, many units would be defective and wasted. Many times throughout the day, quality control engineers take a small sample of the components from the production line, measure the distance between the two holes, and make adjustments if needed. Suppose at one time 4 units are taken and the distances are measured as the 4 measurements we have there. Determine at the 1% level of significance if there is sufficient evidence in the sample to conclude that an adjustment is needed. Assume the distances of interest are normally distributed. Okay, so first, let's note that the average distance needs to be 0.02. So that's going to be our null hypothesis. Anything that's really not 0.02, so whether it's too close together or too far apart, is going to be bad. So we really want our alternate to be not equal to 0.02. So let's go ahead and go here, and let me get off our prior example here. We'll just go down a little bit. All right, so our null hypothesis is going to be that our mean is 0.02, and then our alternate is going to be that the mean is not equal to 0.2. So let me pull up the not equal to symbol. Not equal to 0.02. Oops. And then alpha for us was 1% significance, so 0.01. Now, since this is not equal to, we're going to need to, it's a two-tailed test, we need to divide this by 2. That's going to give us 0.005. And let's notice, back in the original example, there were only 4 pieces of data, so our degrees of freedom is 1 less than that, 3. So let's go ahead and get our critical value by putting those into Excel. All right, so we'll have equal t.inv 0.005 with 3 degrees of freedom, and that gives us negative 5.841. All right, so our critical values and of course, since this is two-tailed, also positive 5.841. Now let's realize, since it is a two-tailed test, anything to the left of negative 5.841 will be in the rejection region, and anything to the right of 5.841 will be in the rejection region. All right, so we now need to do our test statistic. But of course, we don't have the information we need. We don't have the mean and the standard deviation. So let's take our 4 pieces of data and let's put all 4 of these into Excel. 0.021, 0.019. And then my other 2 were 0.023, 0.020. And then let's find our mean and standard deviation. So equal average, and this is in column I, position 1, and column I, position 4 is the last one. So there's my average, and then let's get our standard deviation equals, equal standdev.s, and then again I'm going to tell it I1 to I4, and we get that. And I'm probably going to take that standard deviation out, all of the decimals that I've got. All right, so our mean is 0.02075. .02075. minus the mean that we had up here. And notice I've taken this mean out pretty far to the decimals I have because this is such a small measurement. We want to make sure that we've got as much accuracy as possible in there. And then our standard deviation was 0.001708 divided by the square root of our sample size, which was 4 here. All right, so let's do this calculation in our calculator. On the top, we're going to get 0.00075, and on the bottom, we're going to give us 0.000854, and then let's divide these out, and that gives us 0.878. All right, now, in this particular instance, let's note that 0.878 is neither to the left of negative 5.841 nor to the right of positive 5.841. So it's not in the rejection region. So we fail to reject the null. Now, in this particular instance, that's a good thing. All right, because that means the machine is working properly and it doesn't have to be recalibrated in any way. So let's just state our conclusion. There is not significant evidence at alpha equal to 0.01 to reject the null hypothesis. It appears that currently the machine is working properly. All right, now, while we're here, that would be the end of this hypothesis test. But again, let's do the p-value or the observed significance approach just so we could see how it would be different. Now, we would not be finding these critical values t if we were doing the p-value approach. We would go straight to this test statistic and get 0.878. And if we go ahead and put 0.878 in to get the p-value, recall that that was equal t.dist 0.878. Degrees of freedom, we had 4 pieces of data, so that was 3, and true. And this is 0.7777. All right, so now we need to be careful because this is a two-tailed test and we had a positive test statistic. So remember, with a two-tailed test and a positive test statistic, the first thing we did was subtract this from 1, which gives 0.2223. And then because it's two-tailed, we had to take 0.2223 and double it. So that's going to give us 0.4446. So our p-value is equal to 0.4446. And recall, if the p-value is bigger than alpha, we fail to reject the null, which of course is exactly what our circumstance was here. And of course, in our final statement here, instead of listing alpha, we could list that p-value of 0.4446, showing that that's nowhere near what it needs to be to reject the null hypothesis.